All right, it is 10, so we'll get started. So just to let you know how we're gonna handle things. Nice haircut, thank you. I figure it's about time. Get that quarantine haircut. So I figured just let you know what's in store for us. So as you can see on the PowerPoint, I have the April 9th, so the PowerPoint I made for Friday up. And what we're going to do to try and catch up is I'm going to skip topics in today's PowerPoint. So there's just some things that we're not going to go over for the sake of time. And with that, hopefully by chopping some stuff out, we can catch up where we need to be. At least get started with the PowerPoint I made for today. Just so you know, is my pen working? It is not. 1 second. Must not have it plugged in. I do not. There we go. So Friday, no live lecture. I will record the lecture on Wednesday and have it up for you. And it'll be in the, what is it, 12th, for the Friday the 16th folder. So you can watch at the normal time or just any time, starting Thursday, it'll be available for you to watch. But with that, let's get right into it. Oh, there we go. And we've been talking about orbitals now. We've been talking about our quantum mechanics. And when we were looking at our orbital diagrams on Friday, and just so you know what an orbital diagram is, remember when we were talking about if you're at the first energy level, n equals 1, the only angular momentum quantum number you can have is 0, right? And when you do that, the only m's of L value you can have is 0. And I said every time you make an m's of L, you get to draw a box. And then 2 electrons go in each box. These are called orbital diagrams. And you can see that when we draw orbital diagrams, we put an arrow up and then we put an arrow down, and they're always like half arrows. Each arrow represents 1 electron, and the up and down is another quantum number called spin, m's of S. And now with m's of S, we talked about all 4 quantum numbers we need to describe an electron. So we have the principal quantum number, energy, angular momentum, which is what is the shape of the orbital, m's of L, which is what is the direction of the orbital pointing, and m's of S, which is just called spin. And spin can have a value of +1/2 or -1/2. Spin up and spin down. We don't need to get into like the quantum mechanics of what is spin. The way that I always thought about this is like, what way is an electron spinning? Is it clockwise or is it counterclockwise? In reality, it doesn't quite mean that, but it's a good way for me to remember that. And with all 4 of these quantum numbers, we can learn about a concept called the Pauli exclusion principle. And what the Pauli exclusion principle is, it says that no electron in the same atom can have the same 4 quantum numbers, right? So the quantum numbers is almost like a serial number. It's unique to each electron, or like an address, and only 1 electron can live at that address. So every single electron in an atom needs to have its own unique 4 quantum numbers. That's why for every m's of L, we can have 2 electrons, because if they're in the 1s orbital, which is a principal quantum number 1, L is 0. Remember, 0 is the s orbital. If you only have one value of L, you only have one value of m's of L. And let me just refresh you with how we determine these, right? L can go from 0 to n minus 1. M's of L is minus L to plus L, including 0. Then M's of S, right? That's how we distinguish between 2 electrons that have the first 3 quantum numbers the same. For M's of S, you're either plus 1/2 or minus 1/2, spin up or spin down. So that is our last quantum number there. So, and when looking at orbital diagrams or writing orbital diagrams, you have to have the arrows pointing in opposite direction. That would be incorrect because you're saying both electrons have a MFs of plus 1/2, and that will break the Pauli exclusion principle. So any questions about this concept? All right. And here's a big orbital diagram where we have up to the 5s shell. And we have some other principles we need to know to fill this out correctly. One is the off-ball principle. And off-ball is German for build-up. So any of you who speak German, I apologize for pronouncing that word wrong. But what the off-ball principle says is that when you're putting electrons in orbitals, they always go in the low energy first, and then they build up from there. And here we have our orbitals lined up by energy from low to high. And when you're putting in electrons, you always start low and you just move up to the next electron or next orbital that is lowest in energy. And when we actually do this, what we see is that the 4s orbital is actually lower energy than 3D. And we'll get to this today. We'll learn like how we can memorize this without like actually having to memorize it. But when like filling in electrons, you always fill 4s before you do 3D. And there's another rule called Hund's rule. Hund's rule says if you are in an orbital that has the same energy, so let's say we're filling in the 2p orbital, electrons want to be alone before they are paired up, right? So here we have 4 electrons in the 2p orbital. And Hund's rule says that we have to space them out as best as we can, right? It would be incorrect to put your 4 orbitals where instead of this, that is incorrect. They have to be spaced out. The classic way to remember this is imagine that you're getting on a bus with a bunch of people you don't know, especially during COVID times. You're not going to sit in the same seat as a stranger if there's an open seat available, right? All by yourself. However, once the bus gets full enough, you're probably going to sit next to a stranger than stand, right? So that's basically Hund's rule. You want to be in a seat by yourself, but if you do have to sit next to somebody, then your spin changes, right? You cannot be in the same spin. Questions about that idea? Right. So we're going to just start with learning how to write the electron configuration of elements by using the periodic table. All right. And let's just start, and I'll start with carbon. And what we can see first off, I've color coded these, or somebody has, I didn't do it, but somebody has color coded this periodic table to tell you which orbital goes with which part of the periodic table. So this brown, these are the s block elements or the s orbital elements. Helium's part of that, so that's why I've actually colored helium that brown color. The green is your p orbital elements. Blue is your d orbital, and down here are your f orbital elements. All right, so let's write out the full electron configuration for carbon. And what you do is you start at helium, right? Helium's in the first row, and it's in the s block, and it's the first element of the first row of the s block. So this is called 1s1. All right, we can put one electron there. Then we move over to helium. This is the second element in the first row of the s block. This is 1s2. Okay. But we're not at carbon yet. The goal here is to make it towards carbon, and right now we're at helium. So we continue on because we haven't hit carbon yet. So let's move over. And now we're in the second row. All right, so since we're done with the first row, I can write that down. So carbon is part of the full electron configuration, is 1s, and it has 2 electrons in it. So that's 1s2. Now we move down to the second row. And we're in the s block still, but this is 2s, then 1, 2. Well, we're not the carbon yet, and we're about to go to the p block. So this would be 2s2. Now we make it to the p block. So this is 2p for row 2. 2p1 is boron here, but we're not at carbon, so we move one over. 2p2. All right, we're at carbon, so we're done. And we write down where we ended up. 2p2. So the full electron configuration for carbon is 1s2, 2s2, 2p2. What that means is that carbon has 2 electrons in the 1s orbital. It has 2 electrons in the 2s orbital and 2 electrons in the 2p orbital for a total of 6 electrons. All right, before I'm going to also do AS. But before I move on, questions about what I did there for carbon. All right, let's do AS. We're going to do the same thing. Start at helium. 1s1, 1s, or start at hydrogen rather. 1s1, 1s2. Not at AS yet, but I'm done with the 1s block, so I write that down. 2s1, 2s2. Not at AS yet, but I'm done with this block, so write that down. Move over here, 2p. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Not at AS yet, but I'm done with that row, so I write that down, 2p6. 3s1 for sodium, 3s2 for magnesium, not at AS, but I'm done with the S block, so I write that down. Move over to the P block. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Not an AS yet, but I'm done with the P block. 3P6. Move down to the fourth row. 4S1, 4S2. Now the D block. So what's weird about the D block is that the numbering system is the row minus 1. So we're on the fourth row. So this is 3D1, right? So just remember that. This isn't 4D. This is 3D. So this is 3D1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're not at AS yet, but we're done with the D block. So that's 3D10. Oops. Then once we're back in the P block, we're back with the row number. So this is 4P1, 4P2, 4P3. So the full electron configuration of AS is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Remember, all this is saying is how many electrons we have in each different orbital. So 2 in the 1s, 2 in the 2s, 6 in the 2p, and so on and so forth. Right. So with AS, are there any questions on how we figure out the electron configuration of elements using the periodic table? If not, feel free to try your hand at this with C, D, E, and F. And if you have questions, let me know. Otherwise, I will put up the answers here in a few minutes. All right, so I'm going to start filling these out. If you're still working, go ahead, but I'm just going to start doing C, D, E, and F here. P is 1s2, 2s2, 2p6, 3s2, 3p3, because it ends in the third row, P block, third element. Argon. I was going to tell a chemistry joke, but all the good ones are gone. One of the lamest chemistry jokes there is. Somebody tells it to me every semester. 1s2, 2s2, 2p6, 3s2, 3p6. That's argon. Sodium. 3s1 is where we're going to end up at. 1s2, 2s2, 2p6, 3s1. Then yttrium. It's in the fifth row in the D block. So this is 4D1. Remember, row minus 1. So 4D, then the first element there. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d1. Don't worry, we're going to learn how to like shorthand these because writing all these out is a pain. But these are electron configurations, and that is how you use the periodic table to figure those out. Questions about that? And just so you know, if we have any questions like this on the test, I won't ask you F block. F block is just odd. And F block, you like it starts right here. So 57, 58, then 89, 90. So F block is supposed to be inserted here. But yeah, don't worry about the F block. Just know how to read the periodic table for S, P, and D. We'll be good. Right? So the way to shorthand this is for any element, if they have an electron configuration that is the same as a noble gas, you can just write the noble gas in brackets. So here I'm saying use the periodic table to determine the element corresponding to each electron configuration. So this bracket argon, what that means is that this is shorthand for the electron configuration of argon. So this means argon's right here. So this is 1s2, 2s2, 2p6, 3s2, 3p6. But instead of writing all that out, I can just say bracket argon. So for any element, to shorthand it, you just find the period or the noble gas. Remember, these are noble gases. You just find the noble gas that comes before it, write that noble gas in brackets, and then write the rest of the electron configuration. So here I'm trying to figure out the element that's argon 4s2, 3d10, 4p6. So I go to argon. That's where my starting point is. Then 4s2, 1, 2, 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 3d10. Then 4p6. 1, 2, 3, 4, 5, 6. So this is the electron configuration for krypton. Or, since it's a noble gas itself, these two things are equivalent. Right. So using now our shortcut of just writing noble gas, tell me for B, C, and D, what element am I talking about using the periodic table? All right, so let's start looking at this. So B, we start argon, 4s2, 3d2. The element at 3d2 is titanium. And the fast way to do this is really just look at the last one, right? So I'm saying, what is the element that ends at 5p2? Well, here's row 5. This is the p block. The second element in that is tin. So this is tin. Then what element ends in 5s2? So krypton 5s2, Sr. Ted, so this is why I struggled, Ted, on the homework that I was due this morning because I haven't got this info. You mean the quiz? Thought I would have went over this in the videos that I recorded. Maybe not. But for the quiz, you get 50% for just doing it on time. So I wouldn't worry too much about getting stuff wrong. But if I didn't have that in the video, then I have to relook at those videos this summer. But yeah, any questions on how to do this using our shorthand notation? How do we determine what noble gas to put in brackets? It's whatever noble gas comes before your element. So if I was doing calcium, you just work your way backwards. And the first noble gas I hit is argon. So for calcium, the electron configuration is argon 4s2. So it's whatever is the most is noble gas that immediately precedes it. For like lead, it would be xenon, a lot of other stuff than 6p2, for example. All right. Let's move on then. And one more exercise, just so we have it. Tell me for each of these elements, how many electrons are in the orbitals I'm talking about right there. So for example, magnesium's right here. It's the second element in the 3s block. So that's 3s2, right? So magnesium has the configuration of neon 3s2, which means it has 2 electrons in the 3s block. Right? So one more exercise just to get us completely familiar with this. So I'll give you like a minute or two to figure this out, and then we'll move on. All right. So nickel, how many electrons are in nickel? So the electron configuration of nickel would be argon, 4s2, then 1, 2, 3, 4, 5, 6, 7, 8, 3d8. So that's 8 electrons. Tc, where is Tc? Tc is right here. So and you don't have to write out the electron configurations. I'm just doing it so you can see more examples of it. But Tc is krypton, then 5s2, then 1, 2, 3, 4, 5, 4d5. So that's Tc. Lead, 6p. It is the second element in 6p, so this would be 6p2. Oops. Which is 2 electrons. All right. Any questions about what is being asked here? All right. So we're going to skip this. This is one of the things that's going to be cut. Coulomb's law is how to calculate the energy of attraction between charged particles. I thought you add up all the electrons to get the total electrons that element has. You do, but in the previous question, I was just saying how many electrons are in each orbital, not the total number of electrons, right? So that's why 3s2 for magnesium is just 2 electrons there. Yep. If I was asking how many electrons in the element, then you would. Yep. All right. So let me just briefly tell you what Coulomb's law is. So Coulomb's law is how you determine the energy of interaction between charged particles. And it's based on 3 things. 1, the size of the charge. 2, the distance. That's actually based on 4 things. Now I think about it. The size of the charge, the distance between charges, whether the charges are the same or different, and what's called the dielectric constant. You don't need to worry about dielectric constant or Coulomb's law in general. But what Coulomb's law says is that the closer something is, if they're different charges, the stronger they interact. And the bigger the charge is, if they're different, the stronger they interact, right? So if I have a +1 and a -1 charge separated by 100 picometers, that is weaker than a +2 and a -1 separated at the same distance. That's one thing Coulomb's law says. And Coulomb's law also says, right, if I'm separated by 100 picometers here, this is more favorable than the same charges separated by 200 picometers. Yeah, so this would be on the quiz, right? Because normally I would cover it, but for the sake of time, I'm gonna skip it now. So yeah, that's basically what Coulomb's law says. You don't need to worry about it for the test, but I do want to mention it because you will probably be hearing about it in chemistry. We talk about it in biochemistry, I know that. So just to make you aware of it. Valence electrons is something we do need to look at. Now, valence electrons, there's two types of electrons, core electrons and valence electrons, right? And valence electrons are those electrons in the highest principal energy level. What I mean by that is if we look at fluorine, you have two different energy levels. You have the first energy level and the second energy level. So the highest energy level for fluorine is the second. And any electrons in the highest energy level are called valence electrons. These are the ones that do chemistry. So we have 7 valence electrons in fluorine, 2 + 5. Core electrons are any electrons that are not valence electrons. So fluorine has 2 core electrons. So that's what a valence electron is, and that's what a core electron is. So we're just going to look at how many valence electrons are in our element. So oxygen. You said the second was the highest energy level. It is in fluorine because fluorine only has 2 energy levels, 1 and 2. So 2 is the highest. It's whatever the highest number energy level is the highest energy level for that element. It changes for every element. But let's take a look at oxygen. So the way to really do this, well, I'm just asking for valence electrons. If I was asking for core electrons as well, I would say write out the full electron configuration. For valence electrons, we can just write out shorthand. So oxygen has the electron configuration of helium, 2s2, 2p4. I'll actually just write out, it's 1s2. Writing out helium actually is not any shorter for this. 1s2, 2s2, 2p4. So for oxygen, the highest energy level is 2, and we have 2 + 4 electrons. So oxygen has 6 valence electrons, right? So it's how many electrons are in your highest energy level for that element. So see if you can figure out those numbers for chlorine, sodium, and iron. And I'll give you a few minutes to do that. Wait, 2s2 is more than 2p4. I thought there would be 4 valence electrons. You mean in oxygen? We're talking about the highest energy level in oxygen. That's the second. So there's 2 electrons in 2s, 4 electrons in 2p. 2 plus 4 equals 6, right? All I care about is this number in front, and this not subscript, superscript is saying how many electrons are in each orbital. So that's why it's 6. Our highest energy level for oxygen is the second energy level. I got 6 electrons in that second energy level. So that's why it's 6 valence electrons. So let's look at chlorine. Chlorine has the electron configuration in neon, 3s2, oops, 3p5. The third energy level is the highest. So it has 7 electrons. 2 plus 5 is 7. Sodium, I'll write out the whole thing of sodium. 1s2, 2s2, 2p6, 3s1. Third energy level is the highest. We have 1 electron there. So we have 1 valence electron. Iron. This is the tricky one. And I'm guessing if I put this on the test, those of you who will rely on Google and not think about this will get it wrong. Because when I just checked, when you Google this, Google gives you the wrong answer at the very top. So the electron configuration of iron, let's write out the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 1, 2, 3, 4, 5, 6, 3d6. All right. The correct answer, based on how we've talked about this, is that iron has 2 valence electrons because the highest energy level is 4. So you always go for the highest principal energy level. That's 4 valence electrons. When you Google this, a lot of people, I think the top answer is 6, or it might be 8, which, based on how we're talking about it, is not correct. Beware of random message boards on Google that have other people just randomly answering. But yeah, that is valence electrons. You just see what principal energy level is the highest, and the electrons in there are valence electrons. You did argon 4s2 3d6. Yeah, it's the same thing. If you did the shorthand, you'll get the same answer, right? What I wrote and this are equivalent. It's the same thing. All right. Any questions about that? So for the rest of the PowerPoint, yep. The rest of the PowerPoint, where I'm talking about shielding and penetration, we will just skip the rest of this PowerPoint. So skip that, this, and this. Shielding and penetration is just talking about how electrons can like interact with each other. And for, I would say 99% of you, this is a concept that will never come up again in your lives for the most part, unless you want to go into chemistry. So if you are thinking about going on to chemistry for your career, which is probably a very small portion of you, feel free to go in your textbook and read about shielding and penetration and ask me questions about that. Otherwise, if you're going in any other field, this is probably a concept that will never come up for you. So we will just skip it for the sake of time. So just be aware that when you're studying for test 4, don't expect shielding in effective nuclear charge and penetration questions. Yeah, feel free, to the person who just sent me a message, feel free to like set up a meeting with me if you would like to discuss that. That's no problem. And I think we might call it here. Let me just pop up the next PowerPoint I have for you. Yeah. So on Wednesday, I just want to see how much we have to do to get caught up here. Okay, magnetism. Yeah. So on Wednesday, we're going to tackle what we have for today, what I made for today. And I will see, I want to say one of these PowerPoints is really short, but we'll see. We're going to continue on moving forward. If I make any decision about not doing a reading guide, I'll put that on the announcements. But yeah, I think this is a good time to stop. I'll put a homework up that will go over the electron configurations. So you can have practice on that. Otherwise, I have nothing left for you. So hope you have a good rest of your Monday. Take care.